So I'd like to first say that we're now all of different institutions, and I'd say there's no project lead. There's sort of organic between us, sort of roughly equally distributed the work. So it's very happy to have my co-authors here to also answer your questions and so forth. So I'll start with just describing the people involved. So Scott likes operational semantics. Ramona is doing a PhD on verified compilation. Verified type inferencing is Scott's interest as well. Verified parsing, Michael Norris's interest. Verified x86 implementations and proof producing code generation. You'll see there's a lot of verified, and proof producing here. So really, we are verification people, so to say. And we come here with questions and hope to have discussions. So we don't come with all the solutions. We'd like to really hear from you in this. So please interrupt and ask questions, and we can have discussion. And if you see that we've done something badly, then tell us, and we'll try to do better. And we'll learn. That's what we come here for. Okay. So why, as verification people, why are we interested in ML? Well, because it's a nice, clean, high-level language, of course. We all know that. And it's easy. It has such a nice semantics that it's easy to reason about, informally at least. And this is, then we wondered, could we make this formal reasoning? Is it easy to reason about ML formally? And that's why we are interested in ML. So the purpose of CakeML is to find a subset of standard ML, or mostly standard ML, which would fit this purpose of being easy to reason about. To also have verified implementations of them that are efficient, and have good libraries, and so forth. And then we want to demonstrate that you can actually do a good reasoning about it, and demonstrate that you can that way produce code that you can use. That's a good tool. The CakeML is a good tool in this chain of producing verified code. So the first application as theorem proving / verification people, we consider how can we make proof assistant into trustworthy practical program development platforms using CakeML. So in most theorem provers come with this extract code generation or extraction mechanism where you write your definitions in, say, Coq or Hol4, and then you push a button and you get OCaml or SML code or something like that out. And then you essentially just trust the output. But that was the program you verified. So one of the applications of CakeML is to try to do this more properly with proof-producing translation and then a verified compilation all the way down to machine code. So that's one application of CakeML, which we have almost completely running now. So in this talk, I'll first give you a little bit of background, what we have done. This is the Popple paper from this year, and then the second part of the talk will be about discussion and trying to make the compiler better, the implementation overall. So what's this paper about? This paper was, to some extent, presented last year, so I won't go into too much of that. Last year at the ML workshop, so I won't go into too much detail of that. But I'll just say a few highlights, what it did. So first of all, the problem we tried to solve was that most compilers, verified compilers, attack this angle. So this dimension, how far does the compiler go? So you verify that it's a valid transformation from source code down to something like an intermediate language or bytecode or machine code. And that's one way of describing how far a verified compiler goes. Another dimension is what did you actually verify? Did you verify the compiler algorithm? So is that a function in logic then? Or did you verify an implementation in ML with respect to an operational semantics of ML? Or an implementation in machine code? Or an implementation that's in machine code and can be used dynamically in some larger application? So in CakeML, the Popple paper, the big push there was to show that we can do both dimensions in full. So that's the new thing there. So what is the CakeML language? As I said, it's designed to be easy to program in and easy to reason about formally. In reality, CakeML is roughly standard ML without I/O for the moment and without functors. So there's a lot of research on ML-like languages, and they tend to be very small. So I believe this is a fairly large one for a verification effort. So we have almost everything else. We have higher order functions, mutual recursion, polymorphism, data types, nested pattern matching references, exceptions, modules, signatures, abstract types. Oh, I should say just single level modules. But then, so as a result, it's not so easy to, well, it's easy to program it, but it's not so easy to reason about necessarily. But it's still clean, not always simple. It's grown over time. And since the Popple paper, it's grown even more. So now, as we're trying to approach doing interesting applications, we've also added arrays, vectors, byte arrays, bytes, but very limited support for bytes, just to have them in byte arrays. Strings, also limited support, and here we're automating. We don't have characters, but we do have strings. We have type abbreviations. So, anything in this app. Then we also rework the semantics to make it nicer in many ways, but that's not from the outside visible so much.
As you add more of these base types and things, you realize that when you really want to specify the operational semantics of a programming language, it has a lot of stuff everywhere. Like there's so many different operations that are array updates, byte array updates, all this stuff. So part of the refactor of the semantics was having to deal with, okay, we need to rework out that type for the syntax to be able to accommodate all this stuff. So I think scaling up semantics is part of what we're having to deal with.
There's a really big function. It's a really big function describing the operations on all of the primitive data types in the semantics that is sort of unlike anything you would see in the definition of standard ML, because you don't have the function that says if the array index is out of bounds, then raise this sort of exception. But that's a primitive part of the semantics that just keeps getting bigger and bigger as we add more and more stuff and the next byte groups bigger and more complicated.
So the contributions of the Popple paper were, essentially we have these specifications, we have verified algorithms, and we have a new technique for divergent preservation, and so that's just to show that if the source code diverges if and only if the resulting, the output of the compiler diverges. Bootstrapping, so this is how we got the other dimension. So we compiled the compiler with itself inside the logic, and that way it got verified a theorem about the result of compiling the compiler. And that way we have something about the compiler implementation in a low-level language. But maybe, so that these are sort of techniques, but maybe the most interesting long-term part here is the proof development where everything fits together. Because a lot of research into ML and similar languages tries to target one thing, like something about the type system, the module system, or something like that. But here we really try to get everything in one, and then we have to make decisions about how to get the semantics so that it fits all purposes and makes all proofs convenient, or convenient enough to carry through. So that's one of the big contributions, I think. So what does it look like? A picture. So it's a read-about print loop. We have parser, type inferencer, compiler, and at this level of abstraction, we have a bytecode execution unit, so to say, lexer and garbage collector, big known library also. And this we execute bytecode through compilation into machine code and then running the machine code. So, and this is handcrafted machine code, and that's generated through bootstrapping verified compiler. So this is all just like a high-level picture of what's in the implementation. I won't go into how it was verified. Most of verification of these is standard tactical verification in the theorem brewer. Bootstrapping was then running it inside the logic, which I don't think other people have done. So numbers, everyone asks about numbers. It's very slow. You'll see why later. So our target is actually, it might sound silly, but it is that to be faster than interpreted OCaml. Why is that? Because, although we're compiling, so I mean, we should be able to do that. But it's because we want to compare, because people who use whole light, the theorem brewer we care about, are using interpreted OCaml. So if we can run whole light in our verified setting faster than they do normally, then I think that's a win. So that's what we're trying, but we still have this, twice as fast. So, but we're getting there, I think. So that's future work, and that's where I want your help. So effort as a POPL was about 70,000 lines of proof scripts. This is somewhat random figure because there's a lot of work that's gone before, and a lot of just experience by us on these subjects from before. Size, it's quite big, but that's, and also I should mention, this is a JIT compiler. You know, it produces more instructions at runtime. This is not, it's not fixed, so to say. And this is large due to the bootstrapping, and partly due to the compilation strategy. Okay. So now I'll come to the discussion and sort of in-progress improvements part of the talk. So why is the compiler so bad from a performance perspective? It's because it's a very, very simple compiler, or at least it's structured to be simple. So you start with string, you get tokens by lexing, and then AST, so this is not that controversial. But then we do only a few hops until we get to machine code. So we go to one intermediate language, and then here there's some transformations within that intermediate language. This tries to, this tries to make a few things more uniform so that they're easier to compile. And then this is compiled into a bytecode, which is somewhat stack-based. It is a stack language, essentially. And then that is compiled into x86. And the problems here are, that's a huge leap. That's doing closure compilation and pattern match compilation and everything in one go. And that's another huge leap where there's a lot of data abstraction, again, vanishes. And so the good thing is that this bytecode simplified a lot of proofs, especially to do with the read aloud printed, but made optimization basically impossible. Because here, it's a too high-level language, and it's a little bit too complicated, maybe. It's trying to do too many things. And then here, you lose too much structure already. And then you have to compile each bytecode instruction separately into x86. So you really can't do any peephole optimization around these. So it's very bad from an optimization point of view. So almost no optimizations. Why is that? Because we wanted to make various things more uniform so that it would be easier to prove. It doesn't mean that we couldn't do something better. It just takes more time. And what we want to do now, we have this, but we want to have a better one. But before we sort of embark on verifying a much better, more realistic compiler, we want to make sure we've understood enough to make it a good one. And maybe an extensible one, so that we can then extend it with more optimizations and so forth later. So what we're doing is we're trying to reorganize it into more conventional compiler phases. So we're going to have a lot more intermediate languages. What do these do? Separately module compilation, closure compilation, or declaration compilation, pattern match compilation, all the separate phases. Removal of memory abstraction, register allocation, that's a big new one, which we hope will feel a lot more speed. Everything has separate phases. And then we'll also, previously we only had, currently we only have x86, but we're currently working on supporting multiple backends in one go. And Anthony Fox, who's an expert on these kind of models of the machine languages, he's helping us here. So how far have we got? We're working on it, and we have module compilation, declaration compilation, pattern match compilation, and something to do also before pattern match compilation with pattern matching. And we have some ideas of how to do special treatment for known calls. Currently, there is no special treatment for known calls, which is a very inefficient way. Each time you have to go and do if you call a function f on arguments 1 and then separately argument 2, then it will do actually 2 function applications, right? Well, if you know where f is, then you should just jump to it directly. We also have allocation optimization and register allocation. So this is memory allocation optimization inline. These are shaded because they're not complete yet. And we have this is more sketchy ideas and so forth. And these are almost supported at the very lowest level by Anthony. He's been working on this. So, for instance, if you don't inject some advice, and I'm going to ask explicitly, how should closures be compiled, and where? Where do you think is a good place to do it? Early, late? No one knows. If they're not compiled at all.
Well, how do you compile them?
So,
how do you compile them? Do you use defunctionalization or do you do closures of them?
Robin has to answer.
Well, Milton style or more conventional?
Conventional. Yeah, we're not. Well, thus far, we're not copying any code to try to do crazy Milton, super optimized things. We're just putting a closure record into the heap somewhere. Well, I mean, I can explain further what we do, but I don't think it's a very good strategy. It needs a more principled approach, but essentially in that intermediate language, we go through and annotate the expressions themselves with just enough information about the bodies of the closures to say like what the free variables are. Like, it's just information for how to build a closure record. And then the compiler emits a sequence of bytecode instructions that will build that closure record. And we compile all the bodies of the closures separately and have labels so that we can put a code pointer and jump to it. So it's the most straightforward thing you could think of. It's pretty terrible.
So I guess the question is, how are you identifying your bottleneck? And do you know the closures of the bottleneck?
Well, one definite bottleneck is that in doing this naive pass, since ML doesn't have multiple argument functions, if we want to apply a 2-argument function, we create a closure in the interim. So we have to do better than that, clearly, if we want to get any performance. But how does doing better on that interact with the general way that you're doing closures is something I don't think we know the answer to, although the answer may be it's part of folklore in ML compiler implementers. I don't know.
So the usual thing people are doing is to introduce an intermediate language where you have multi-parameter functions, and then you have optimizing phases on that thing before you decide on closures.
Arity base everything in your intermediate language.
What's that?
Arity base everything, so you've got multiple arguments, multiple argument instructions.
I think we do have multiple argument functions in our intermediate language, but they're not used. But we don't have multiple returns, and so yeah, that might be.
Something we've been discussing among us, should we do land lifting and where and so forth. That's also part of that. Could easily do it very aggressively, but doing a very aggressive land lifting is also can be dangerous.
Just one observation first, with Gershon Bias doing some work in the account that addresses this sort of problem and was being thought about sort of from scratch, so it might be worth it.
Okay.
I think the answer to that question is yes.
Okay. But not, or is it everywhere, or
by dangerous for like aggressive lifting? Do you mean dangerous in terms of difficulty in verification, or do you mean dangerous in terms of the quality of the code you generate?
Dangerous in quality of code.
Okay.
As in, if you do it everywhere blindly, then you get bad performance.
Just general. Okay.
So, questions? So, where should we, because at the moment, our current thinking is just to get the whole compiler going, as in get through all these intermediate languages and then hopefully have good definition in between so that we can do optimizations later. But first, just to get a good pass through. But then a question is, where should we focus our attention? Where can we get the most performance out of it? Because suppose we just have no optimizations through this chain of conventional languages, where should we focus our attention to? Because I'll say verifying correctly of optimizations is expensive in terms of effort, so we'd like to know where we should put that effort and get maximum reward.
So I think usually from the experience from Big Blue and the ML Kit compiler and these things, so inlining and specialization of recursive functions, that's probably one of the optimizations that will give the most. Of course, it assumes that you can deal correctly with known functions and multi-parameter functions, but those are the optimizations that really changes the degree of speed.
Inlining?
Inlining and specialization of recursive functions like maps. So you just specialize the map whenever you see it, and then you have a special version for that. Then you automatically get inlining of the function you pass in, and you really get the machine code with the add one or whatever.
To make it less hierarchical.
Yes.
I think one thing to add to that is that inlining is often effective because you eliminate allocation, not just because like a static branch these days is basically free, whereas like if you have to do an allocation because like your calling convention requires this or something, that's the stuff that we're looking at.
Yeah. Okay.
Do you have a corpus of code that would traditionally we use a compiler itself to use that as the first code base to optimize?
Yes.
Presumably CakeML is not written in CakeML, right? So
we get that.
That's how we do the bootstrap.
The bootstrap.
oh, fantastic! So would this be a good source of optimization possibly by tracing through CakeML?
Yes, it's where you do evaluation within the theorem program. It doesn't really give you too many hooks to grab, but yeah, it's definitely you can look at the code and see.
Well, we can do evaluation outside of the VM program as well.
Yes. So just observations from a verification point of view that doing optimizations in intermediate language with Lambda has the complexity of having the state relation between source and target is quite hard to define because the code exists in the values too. And in the lower levels, you have another problem of then you have to be constantly interfacing with the invariance of the copy GC. So there's a nice sweet spot actually in between when you have a first order language, but you don't yet have the GC visible. So there's something nice there, but we believe we have to deal with both of these to get optimizations. That's just an observation. So I think I'm running out of time. Okay. So we're also wondering, maybe offline we can talk about, we're wondering, we want good libraries, what should these be? Should these follow SML? We've followed SML quite a lot, but is that really the right thing to do? That we should talk about offline. And large examples, cool examples that we could verify, and there's some value in the verification. We'd be interested to hear if you have some ideas. I'll skip this. So, as I said, one of the big examples is verified by light, running on a verified CakeML. And also, we're looking into a connection to the SCL4. And for this, we want a foreign function interface. We have some ideas of how to do that. It would be very simple byte array interface initially with Oracle semantics, and essentially this interface would be connected directly to the IPC mechanism. visiting them later this year. Try to get this running. I think I'll end with that.
Yeah, we're taking questions here at the top, but we have time for one quick question or question.
You said you don't support photos. So how far, what's the issue and how far away are you from that?
It's not a technical issue. It's a matter of sitting down, writing. It's not a technical issue. It's a matter of sitting down, writing the declarative type system rules for the functor, doing the type soundness proof, and then making the type inferencer and the type inferencer soundness proof work in all of that well. That's a complicated, that's just a lot of work, and you can see we've got a lot of work to do, and it just has never really got near the top of the priority stack. So the way we prioritize things is if we have a cool application that we want to support, and that application requires something that we don't have, like decent performance or byte arrays, then we work really hard to get that in, and sort of we have to be sort of ruthlessly pragmatic in that sense. You know, we're verification people. Of course we want to be pragmatic.
And one last question from Marshall.
I was just going to observe that your runtime value representation can make a big difference to your performance, because like you tend to sort of do a lot of examining and traversing values, so you have sort of expense every time you do that. The other observation was just that for the same about interaction with the GC, if you optimize heavily enough, maybe you can just eliminate allocation in large blocks. And if you don't let the GC run during that time, you don't need to work.
Yes. Yeah. The thing is that the semantic still talks about the GC. So you have to, it just complicates the semantics of this. And then you have to prove that it doesn't matter in certain places. Okay.
So it sounds like you have a number of interesting problems that grad students who want to do internships during their PhDs might join to formalize functors, for example. So I think Gabriel has volunteered. But let's.
We have a big page of examples of internship student-sized projects out of CakeML.org. So if you want to come and work with us, we desperately could use more manpower.
There you go, wonderful. The power of open source. So we're ready for the break now, so let's thank the speakers for a wonderful talk. There'll be a break until about 11.